Carry a ball from a high shelf to a spot on the floor across the room. Take any route you like, one long sweeping arc or straight down and then across the floor. Gravity acts the whole way, and the gravity does work. Here is the remarkable fact. For gravity, every route gives exactly the same work. For friction, the route changes everything. That one distinction splits every force in mechanics into two families, and it comes down to a single test on a single integral. Start with the bookkeeping. A closed system exchanges energy with its surroundings and nothing else. The principle of conservation of energy says that when a system and its surroundings move from an initial state to a final state, the total change in energy is zero. The change in the system's energy plus the change in the surroundings' energy adds to zero. Whatever energy the system loses, the surroundings gain, and the reverse. Every transformation we track, inside the system or across its boundary, must balance this ledger. Our first account is mechanical energy, which comes in two types: kinetic energy, the energy of motion, and potential energy, the energy of position. Kinetic energy we already know how to compute. Potential energy we have not yet defined, and defining its change precisely is exactly where this chapter is headed. That definition will hinge on one property of work. Recall the definition of work. A force F acts on an object as it moves along a path, from initial position R sub I to final position R sub F. The work is the integral along that path of F dot dr. At each infinitesimal step, take the component of the force tangent to the path times the displacement of the point where the force contacts the object and sum along the route. Work is, by construction, a path integral. So before potential energy can be defined, one question has to be settled: whether the value of this integral depends on which path the object takes. Here is the test case: an object moving under gravity near the surface of the Earth. Both trips start at the same point on the vertical axis, at height y sub I, and both end at the same point on the horizontal axis, at x sub f. Path 1 sweeps from start to finish as a wide arc. Path 2 takes two straight legs. Leg A drops from the start straight down to the origin, then leg B runs from the origin across to the finish. Gravity is the same everywhere along both roads. Force equals negative mg in the j-hat direction, magnitude mg pointing straight down. Take path 1 first. At any point on the arc, an infinitesimal step is dr1, dx1 in the i-hat direction plus dy1 in the j-hat direction. Dot this step with the force. The force has no i-hat part, and the j-hat dot i-hat is 0, so the horizontal term dies. Only the vertical term survives. F dot dr1 equals negative mg dy1. The whole sideways sweep of the arc has already vanished. Now integrate along the path. The work W1 is the integral of negative mg dy1 with the height running from y sub I down to 0. Since mg is constant, that evaluates to negative mg times the quantity 0 minus y sub I, which is positive mg y sub I. Positive makes sense. Gravity points down, the object ends up lower, so gravity helped. And look at what the answer contains: the mass, the gravitational field strength, the initial height. Nothing about the shape of the arc survives. Now path 2. One leg at a time. Along leg A, the object moves straight down the vertical axis, so each step is dr sub A, dy sub A in the j-hat direction, and the integral is the one we just evaluated over the same height range, so w sub A equals mgy sub I. Leg B runs horizontally, so each step is dr sub B, dx sub B in the i-hat direction. Dot with the force, negative mg j-hat dotted into dx sub B i-hat is 0 because j-hat dot i-hat is 0, so w sub B is 0. No surprise, leg B is perpendicular to gravity, and a force perpendicular to the motion does no work. Now add the legs. W2 equals w sub A plus w sub B mg y sub I plus 0. The total work along path 2 is mg y sub I, exactly the value along path 1. Two very different routes, one identical answer. Here is why the route can never matter for gravity. Approximate any path at all by a staircase of tiny steps, each one purely horizontal or purely vertical. Every horizontal step is perpendicular to gravity. It contributes 0. Every vertical step contributes negative mg times its height change. Count those height changes with their signs. A detour that climbs and comes straight back down does negative work going up and exactly the opposite coming down, so it nets to 0. Extra horizontal steps are free. Extra vertical ones cancel in pairs. What survives is the total drop from start to finish. Only the change in height is ever built. Now the contrast. Kinetic friction. An object slides along a surface. The coefficient of kinetic friction is mu sub k and the normal force is n. So friction has a magnitude mu sub kn, and it always points opposite the motion. First route, slide straight from x sub I to x sub f. Friction points backward the entire way, so integrating the force component along the route gives negative mu sub kn times s1, where s1 is the path length. On a straight path, the length equals the displacement delta x, so the work done by friction is negative mu sub kn delta x, negative, and set by the distance traveled. Second route, same two endpoints, slide past x sub f, overshoot by a distance d, then come back. Friction always opposes the motion, so it opposes the motion on the way out, then reverses, now pointing right, and opposes the motion again on the return. Its work is negative on every leg, nothing cancels. The total is negative mu sub kn times s2, where s2 is the full distance traveled, delta x plus d on the way out, plus another d coming back, so s2 equals delta x plus 2d. That is strictly greater than delta x, so the magnitude of the work is strictly larger on this route. Friction's work depends on the path traveled, not just the endpoints. Put the two experiments side by side. Gravity, path 1 gave mg y sub I and path 2 gave mg y sub I. Different routes, identical work. The result depends only on the endpoints. Friction, the straight route gave negative mu sub kn delta x, while the overshoot route gave negative mu sub kn s2, a strictly larger magnitude. Same endpoints, different work. And do not read the distinction of the sign. Carry the ball upward instead of down, and the gravity's work turns negative. Yet it is still identical on every route. The distinction is whether the path matters. We are looking at two fundamentally different kinds of force. That test earns a definition. Whenever the work done by a force in moving an object from an initial point to a final point is independent of the path taken, the force is called a conservative force. Gravity near the Earth's surface passes the test. Conservative. A force whose work does depend on the path, like kinetic friction, is called non-conservative. This single property is what will let a conservative force store energy as potential energy, the idea this chapter builds toward. The complete argument in 3 moves. Energy bookkeeping. In a closed system, whatever the system loses, the surroundings gain. The total change is 0. Work, it is defined as a path integral, so it could in principle depend on the route. The experiment, gravity's work equals mg times the drop in height on every route, while friction's work grows with every extra bit of path. Path-independent work is the defining mark of a conservative force, and that mark is the doorway to potential energy. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.